thesis for defense. The aim of this thesis is basically to study the global structure of certain graphs that are tree-like in construction when they become large. Basically, we applied techniques that are the intersection of probability theory and then combinatorics, which have been developed in the last 2 decades. So basically, we would be considering a sequence of discrete objects, say Mn, converging to a continuous object, say M. When such a limit exists, there can be deductions that could be made as follows: that if there's a mathematical property P that satisfies all M's, and there remains invariance under the limit, then the continuous object M satisfies the property. If the property P is satisfied by the continuous object M and remains invariant under the limit, then all Mn satisfied approximately for large N. And another important consequence is that of what we call universality, that if there is another sequence of discrete object Nn that converges to the same continuous object, then we can deduce that these Mn and Nn share the same property for large N. Now, in our context, a mathematical property could be some dimension or an extremal statistic. Now, our discrete objects will be the so-called planar maps. By definition, we will define a planar map as a connected plane graph that is embedded on a 2-dimensional sphere up to continuous deformation. Now, as usual, our planar map would have a vertex set and an edge set. But also importantly, it would have faces, which are the connected components of the complement of the map. Now, we would assume what we call stereographic projection. So then it would make sense to consider embeddings on an infinite plane. In that case, our planar map would consist of a finite number of bounded faces and a single infinite face. By convention, we would root our map at an edge that is on the boundary of the infinite face so that our infinite face lies to the left. So this is an example of a planar map that has 6 bounded faces. And the face, a bounded face is, for example, the color section. Now we will view our objects as metric space valued random variables, and we will call them random planar maps. In that sense, this particularly the metric space equipped with the usual graph distance. In that case, we could define, or we could give the classical definition of convergence of distribution, or the so-called weak convergence, and use this as our notation, a D on the long arrow as a convergence distribution. And the notion of convergence will be that of the convergence of compact metric spaces for the Gromov-Hausdorff topology. Now, by definition, the Gromov-Hausdorff topology, the Gromov-Hausdorff distance between 2 compact metric spaces, say X1 and X2, can be thought of as isometrically embedding these 2 spaces on a common space and then comparing their Hausdorff dimension in some sense. All right. Now, I would introduce the limiting objects that are of interest to this thesis, but then I would make a recall on the so-called Bianemi-Galton-Watson tree. Now, the plane trees are of importance to this thesis. Basically, you could think of a plane tree as a planar map that has a single face. But then also we can also think of a plane tree as a genealogical tree, so that a vertex in the plane tree is a member of a population of this tree. And the genealogical tree, basically, that is starting from a root, a distinguished vertex we call the root, which we will denote by the empty set. Now, we define a sequence of probability we call mu, and then we introduce some randomness to plane trees via a branching process called the Bianemi-Galton-Watson process. So that the Bianemi-Galton-Watson tree with mu, which we would call the offspring distribution, would be a random tree tau, so that the number of children of the roots is distributed according to mu. And then conditionally on the event that the root has I number of children, then the number of children of the I children are independent of the law of mu, and so on. Now, size conditioned Bianemi-Galton-Watson tree is well studied. that was pioneered by David Aldous in the 90s, who stated that when mu is critical, that's when the mean of mu is 1 and has a finite variance sigma, then a Bjarne-Migart-Watson tree Tn that is conditioned on the number of vertices after proper rescaling converges to a certain compact metric space we would call the Brownian continuum tree, Te. Now, the version of Brownian continuum tree we consider are those that are constructed from a normalized Brownian excursion by a process we call gluing. Now, this requires defining some pseudometric dE and then taking this quotient, which involves taking the unit distance and identifying points in this distance that are equivalent and that the equivalent relation generated by our pseudometric as such. So this is a simulation of a Brownian tree. Now, points on the Brownian tree can either be a leaf. In that case, when I eliminate a leaf, the Brownian tree remains connected, or it can be a branch point. In that case, when I eliminate a branch point, the tree is disconnected into 3 components. So in some sense, you can say that the Brownian tree is binary in some sense. Now, Thomas Buchan generalizes Aldous' theorem in the sense that he considered mu to be in the domain of attraction of a stable law, specifically affix alpha in the interval 1 to 2, and then define mu approximately to ck to the power -1 minus alpha for c greater than 0. Now, he proved that the Bjarne-Migart-Watson tree with such an offspring distribution conditioned on the number of vertices after proper rescaling by the given constant converges to another compact metric spaces that we call the stable tree of index alpha, which was introduced by Legal and Lejeune in 1998. So basically, this is a simulation of a 1-1 stable tree. Now, the stable tree is qualitatively different from the binary tree in the sense that it has a countably infinite number of vertices that has infinite degree. These branching points are those indicated in the deep blue colored. Yes, that's the yeah. So another important limiting object we consider is the stable loop tree. Now, one could think of a stable loop tree as being constructed from a stable tree by replacing the branch points by cycles that are proportional to the width of the branch points, and then arranging them in the tree structure as we have this. This object was introduced by Kurian and Kochemsky, and in that work, they gave an invariance principle that provides the sufficient condition on which a discrete loop tree assigned to some tree converges to the stable loop tree. So in general, the aim of this thesis, or the goal of this thesis, is to choose randomly elements of certain classes of map that are tree-like by construction, rescale the graph metric by a proper constant, and then look at the limit in the sense of Gromov-Hausdorff topology. Another goal is to understand how the continuum random tree, we call CRT, and the stable loop tree appear as scaling limits of random maps that are tree-like. So I'll zoom on to our contribution. So our first contribution had to do a model we'll call the Hailing-like maps. So Hailing-like maps will be constructed from a plane tree by assigning marks to the corners of some vertices, and then connecting the marks by a single edge along the contour of the tree. So for this specific example, we have all the corners, all the marks assigned to the corner of the leaves, the corners of the leaves, and then generating this map. But then we restrict ourselves to 2 particular conditions. Now, in the first condition, we assume, or we consider the case where each vertex is assigned or exactly one corner of each vertex is assigned a mark, exactly one mark. So in that case, we call H0 our skeleton tree, which would be a non-crossing tree, and then the equivalent map will be the so-called non-crossing intersection. In the second condition, we would mark at least one corner of each of the vertices of the plane tree, and then the resultant would be the so-called non-crossing outer planar map, whose two connected components are non-crossing dissection. Now, we will sample an element in the sets of Haley-like maps with n-bounded faces according to a probability measure that is proportional to the weight of the map. The main weight is basically would be defined as a product of certain weight face weight indexed by the degree of the faces of the map, as you can see. And it will be normalized by some persistent function we called Zn that we would ensure that is greater than 0. Now we would apply some useful correspondence or bijections. So for a non-crossing dissection, we consider the so-called weak dual. This will be constructed from the dual. The dual basically is assigning a vertex in each face and connecting vertices if the faces are adjacent. But then in our case, we consider weak dual where we erase the vertex in the external face and then all the edges is connected to the external face. But then later, we also consider an augmented weak dual, which we obtain by replacing the edges. But then in this case, each edge is associated to a single vertex in the outer or in the external face. This is the case that we have a non-crossing dissection. Now, in the case C hashed, where we have a non-crossing outer planar map, we apply a construction in the literature called decorating trees, or trees that are decorated, or what's also people call the enriched trees. So in this case, the map would be associated to an underlying tree, which whose inner vertices are basically the cut points of the map, and then other vertices are the leaves. And then the inner vertices, or the vertices, will be decorated by a sequence of vertices, a sequence of non-crossing dissections that are actually adjacent at the cut points. But then, of course, we don't see any decoration on the leaves because we would denote those decorations there as an empty decoration. Now, Kochemsky and Mazuk defined or proved the law for the shape of a non-crossing tree sample that's sampled according to the probability measure I mentioned earlier on. They proved that the law is the so-called modified Galton-Watson tree with offspring distribution mu, not mu root, and then mu. In this case, the tree receives the root of the tree receives offspring according to mu root, and then other vertices receive offspring according to mu, with mu not mu root and then mu defined as such. Okay. Now, what were our results? Now, in the case where in case 1, we would view our weak dual tree as a size condition modified Galton-Watson tree given by that, and then we prove that if there is a B. Now, it's very important because to choose a B in that interval, because in that case, the measures, the offspring distribution become probability measures, and you can also choose it in a way that the mean of the offspring distribution is critical or subcritical. Okay, so if B is chosen in the interval such that our mean is 1, and then the offspring distribution has finite exponential moment, then after proper rescaling, we have a convergence towards the Brownian tree in the group of halves of sense. The idea of the proof is based on the Markov chain argument that was introduced by Kurian, Haas, and Kochemsky, along with using the scaling limit of the weak dual tree that probably was studied by Kochemsky and then Mazuk. Okay. Now, in the same case, C star, if there is a B in this interval with mean one, so that the offspring distribution has mean 1, and mu belongs to the domain of attraction of a stable law, then there is a sequence Bn that converges to infinity so that we obtain a convergence towards the alpha stable loop tree. And here we apply the invariance principle that was proved by Kurian and Kochemsky that gives, that I mentioned earlier on, alongside estimating the Gromov-Hausdorff distance between the non-crossing dissection and the loop tree of its withdrawal. In the second case, C hashed, we will view our non-crossing outer planar map as a size-conditioned Bialy-Galton-Watson tree decorated by phase-weighted finite sequence via non-crossing dissection. And in that case, if mu satisfies some suitable admissibility conditions, these admissibility conditions will be basically given in terms of the offspring distribution, or the maximal mean of the offspring distribution of the underlying tree. And then we see in the proof that this condition turns out that the offspring of the underlying tree has a finite exponential moment. And then in that case, we have a convergence towards the Brownian tree in the Gromov-Hausdorff sense. In this case, we apply some general theorem that was given by Stufler, which holds for random decorated trees, satisfying some certain condition. Now, if mu is under the same C hatch, if mu is heavy-tailed with index alpha in the interval, so that the offspring distribution of T satisfies some suitable criticality and regularity conditions, then there exists a sequence of constant Cn such that the proper rescaling, we have a convergence towards the alpha stable loop tree. In this proof, we use a general invariance principle for decorated trees that was introduced or proved by Delphin, Stephanson, and then Stufler. Okay, so this was our first contribution. Our second contribution had to do with so-called series parallel maps. So by definition, a series parallel map would be constructed from a plane tree by repeatedly subdividing edges or doubling edges. Now, in our work, we are interested in two connected series parallel maps, which, for example, is given as such, and then we route it in the usual way as such. And then we will view it as an orientation-preserving homomorphism of the plane. We consider also an associated structure we call networks. So a network will be one of these, which are series parallel. But then on the left-hand side, we have a series parallel graph that is not too connected. And on the right, we have a one that is too connected. Now, the one that is not too connected, we will refer as a series network. And then on the right, we will call the parallel network. But then we note that in both cases, when I join these two distinguished points, we will call poles, north and the south pole, we obtain a two connected SP graph. Now, I mean, the usual question we would ask is what happens as the number of edges of our objects increases. So from 13 edges down to, by simulation, down to 2,352 edges, we could see that as the number of edges increase, the graph become tree-like in some sense. Now, another good observation is that also as the number of edges is increases, the poles also gets closer and closer. The north and south pole gets closer and closer. So by notation, I summarize the notations in the theorem here. We will denote NN by the set of SP networks with N edges, and then SPN as uniform elements in NN, and then SPN with a subscript mu to be the weighted version, of course, which is 2 connected by a measure mu. Specifically, the mu we consider here is viewed as a critical offspring distribution of a Bianemi-Gauss-Iguassen process with finite exponential moments. And of course, we will call T as a uniform plane tree with n leaves and no vertex of out degree 0. Okay, so here our result was as follows. So we proved that after proper rescaling, there is a constant C mu that after rescaling with the graph metric, we have a convergence towards the Brownian tree in the Gromov-Hausdorff sense. Now, in our paper, for concreteness, we work with random parallel networks. But then it can be observed that this proof can be adapted to the series network, and of course, the series parallel maps. Okay, so these 3 steps is basically the strategy of the proof. So first, we have a bijective method that gives a correspondence between the Tn, a set of uniform trees, and SP, and a set of uniform SP graphs. Now, the second step would be finding a scaling limit results for Tn. But then, fortunately, Korczewski had developed this or proved this convergence of Tn for here we notice that here the conditioning is on the number of leaves, the convergence towards, we obtain a convergence towards the Brownian tree. And then finally, we show that the Gromov-Hausdorff distance between Tn and SPN converges to, for example, 0 in probability. Right. Now, I'll just briefly describe the bijection we consider here. So here, the trees we consider are labeled trees. So for example, we will label a tree P. If a tree is labeled P, then all non-leaves that are in even generations are labeled P, and all non-leaves in all generations are labeled S. In the opposite way, if a tree is labeled S, then all non-leaves in the even generations are labeled S, and all non-leaves in the odd generations are labeled P. But then in this example, I do that with a tree labeled with P. So here, what we do is we assign edges. So the bijection gives a correspondence between T and a set of trees with N leaves and a set of parallel maps with N edges. So then we assign an edge to each of the leaves and compose them as follows. So you consider the leaves, and then if it is the associated parent is labeled as, we compose them in the series fashion. Okay, if its parent is labeled as is composed in a series fashion, its labeled P is composed in a parallel fashion. We go this, we go that, and then eventually we obtain our SP graph, which has n number of edges. Now, of course, the technique of the proof relies on the Markov chain argument that was introduced by Korczewski and it also, and the other one I forgot. Yeah, but then we rely basically on a decomposition structure of our graph, which we call a blob decomposition. So here we have a plane tree in the middle here, and then we color the roots, and all roots, all vertices in the even generation that has at least one child also red. Now, doing this would decompose the tree into maximal subtrees. These are the maximal subtrees are the ones that are colored. We will call segments. Now, the corresponding maps associated to the segments are what we will call blobs, basically. Now, the blobs have special properties in the way that a geodesic between two vertices in the same blob is entirely within the blob. And also, any geodesic traversing a blob enters and exits through either the North Pole or the South Pole. So these are the important remarks that allows us to prove results in the theory. Okay. All right. So to complete, I would have to mention that several planar maps have been shown to converge to the Aldous CRT. For example, the uniform stack triangulation with two end faces was proved by Albanks and Marquette to converge towards the CRT. Janssen, my advisor, and Stefansen, my advisor with Svante Janssen, also proved that the Boltzmann type bipartite maps, the bipartite maps are basically the maps that has all faces being an even number with n number of edges and having a face of a microscopic degree also converges to the CRT. Alexander Seracini also proved that the uniform outer planar maps with n vertices converges to the CRT. Kurian-Haas and Korchevsky proved that random phase weighted dissection also converges to the CRT. So we believe that results from our paper significantly add to this list. So thank you. So maybe this is also an opportunity to celebrate